In this video, we're going to be talking about two separate issues, but both of them are really quick, so I'm going to squeeze them into one video. One concept is called the special parallel line theorem, and so we've been talking about ratios and proportions and similar polygons, similar triangles, so this kind of fits in with that. Let's look at this triangle right here. Again, if we break this up into two different triangles, which we're going to do in a second, then we can compare some proportions. Let's get these parts labeled. Alright. So if I create my two different triangles here, my smaller one here, which is PAQ, that tiny one on top, and if I draw the bigger one, which is triangle ABC, then we have two similar triangles here. They have a scale factor. Let's say that I knew that this was 5 and this was 5, this was 7 and that was 7. Then if I fill in the side lengths for each of my triangles here, the tiny one is 5, right? But the big one is the whole length here, so that's 5 and 5 together, which creates 10. So if we set up a proportion and a ratio comparing these corresponding sides here, we get 5 over 10, and that simplifies to 1/2. So our scale factor is 1/2. If the scale factor is 1/2, this is a special relationship here, then there's some shortcuts we can take. We actually don't have to break these triangles up. We don't have to compare proportions. There is a really quick shortcut we can take here. Let's say that we knew that BC was 6. Since we know the scale factor is 1/2, and if this segment PQ here is parallel with the bottom segment BC, then PQ is always going to be half of what BC is. So PQ would be 3, right? PQ is 3. So there's a couple of ways we can think about this. One is that P is right in the middle here of AB. So P is a midpoint. So if we have a segment that's joining the midpoints of two sides, so PQ is joining the midpoints, P and Q, right? And the scale factor is 1/2. And if PQ is parallel to BC here, if this middle line is always parallel to the outside line, or the outside line is always parallel to that inside line, or the inner line, then this relationship is always going to be true. That the outer line, the line on the outside, is always going to be twice the length of the inside, or we can think about it the opposite way. The inside is always going to be half of the outside. So basically that's it. So three things have to be true. The inner segment has to be basically joining midpoints on the outsides. These two lines have to be parallel, and the scale factor has to be 1/2. If that's true, then we're allowed to say that this inner line is always half of the outer line, and the outer line is always twice the inner line. So it seems more complicated than it really is. So let's do some practice here. If I know that this segment is 6, this segment is 8, and if I know that these two segments are equal, well then this one is 6 as well, which makes the scale factor 6 over 12, which is 1/2. So that part's true. Say we know that's 8, and it's equal to this one, so that must be 8. So again, we still have a scale factor of 1/2. We now know that this line is right in the middle of the outer edges right there. Those are midpoints right there. So since we know the scale factor is 1/2, this line is right in the middle, and it's also parallel, then it's going to be, oops, we forgot our letters here. That might make a difference if we're solving for something. So we know that the inner line is going to be half of the outer line, or the outer line is twice what the inner line is. So if this inner line is 8, the outside must be twice that, 16. And again, over here, let's do another example. Let's kind of make it a little bit more complicated. If I know that the outer edge here is 8, the total here is 8, and I know this much is 4, and if they're equal lengths, then this must be 4 right here, right? Okay, so far we got a scale factor is 1/2. Let's say I know that that's 5, and that this is also the same, so again, another scale factor of 1/2. A, B, and C. We're going to say this tiny triangle is ABC. The outer triangle here is going to be XYZ. Now we can solve for some things here. We can solve for BC. So this line right here, if we know it's parallel to the outer edge, then we know it's going to be half of this. Well, if the total is 8, then half of it must be 4. So BC is 4. Let's solve for YZ. So YZ is this entire segment on the bottom here. Let's say that we knew that AB was 3. Well, if it's parallel, and if the scale factor is 1/2, and if A and B are midpoints, then this segment is going to be half of the outer edge, or the outer edge is going to be twice the inner segment. So the outer segment must be twice 3, which is 6. So let's say that C is a midpoint as well, so that must be 3 here and 3 there. If the total is 6, like we just said, and C is in the middle, then each of these smaller segments are half of 6, 3. Solve for another one here. AC, let's say that we knew that AC is parallel to this outer edge here, XZ. Well, if we know that half of it is 5, the total must be 10, and that must mean that AC, which is half of 10, is 5. Let's look for some perimeters here. The perimeter of ABC, so we're talking about the tiny triangle here. Well, now that we know all of the values, AC was 5, AB was 3, and BC is 4. The perimeter is just adding up all these outside edges, so 3 plus 4 is 7, plus 5 is 12. So the perimeter of ABC of that triangle is 12. Let's find the perimeter of another shape, quadrilateral ABCY. So when you're asked to find the perimeter, you're given pretty much the outer edges. You're given the corner values right here with the letters. So ABCY, and if it's a full shape, we got to connect Y to A. So this quadrilateral right here. Well, we know AB is 3. Oops, 3. BC is 4. So we're going to be adding up all these edges here. YC is 3. And AY right here is 4. So add those all up. We get 7 plus 7, that's 14. Alright, so basically, recap that. If we know that the outer edge is parallel, the outer segment is parallel to that inner segment, and the scale factor is 1/2, and that inner segment is connecting to midpoints, we can take that little shortcut, say that the outer segment is always twice the inner segment, or the inner segment is always half of the outer segment. Alright, let's move on to the next thing here. So not really related except for the fact that we're talking about triangles. Triangle inequality theorem basically tells us how a triangle can be formed, what the lengths of each segment have to be in order for it to form a triangle. So the first statement is that the smallest angle Smallest angle is always across from, or opposite, is across from the smallest side. So let's say that we knew some side lengths here. We know that, let's give it a title here. This is a triangle XYZ. XY is 9, XZ is 13, and YZ is 15. Well, if the smallest angle is always across from the shortest side, then we can find the smallest angle by looking at the side lengths. So XY happens to be the smallest length on this triangle, right? So across from it must be the smallest angle. So let's order the angles from smallest to largest. So angle Z right here, angle Z is the shortest or smallest angle. So let's find the next smallest side. The next smallest side is 13. So what angle is across from that side? Angle Y. So angle Y is the middle angle there. And let's find the next size. 15 happens to be the biggest. What's across from 15? Angle X. So angle X is the biggest angle. Alright, so taking that concept, we could apply it in a slightly different way. We could go the opposite way. If we knew the angles, we could find the lengths of sides in order. So the smallest side is across from the smallest angle. So let's label this one K, L, and M. Say that we know that K is 67 degrees, L is 59 degrees, and M is 54 degrees. So let's name the segments from smallest to largest, knowing the angles now. So what's the smallest angle? Angle M. What's across from angle M? Segment KL, or LK. That's the shortest side. It's across from the shortest angle or smallest angle. What's the next one? 59 degrees is the next size up. So across from that must be the middle length. So KM is our middle length. And across from the biggest angle is 67 degrees, or angle K, and across from that is LM, or ML. So segment LM is the longest side. It's across from the biggest angle. So if we kind of sum that up, and then we have this next theorem. The sum of any two sides must be greater than, we're going to use an inequality statement here, greater than the other side. Come on now. The other side. So what does that mean? Well, let's look at some values of a triangle here. The values of the lengths of the sides here. If I have a triangle whose lengths measure 3, 4, and 5, well then the sum of any of these two sides must be greater than that other side. So let's try it out here. 3 plus 4, that's the sum. That has to be greater than the next side. Well, the next side is 5. Is 3 plus 4 greater than 5? Yeah, that checks out. Let's check another pair here. 3 and 5. Let's say 3 and 5, if we add those up, that has to be greater than the other side. Well, the other side is 4. Is 3 plus 5 greater than 4? Sure, 8's greater than 4. Okay, so that checks out. Last one here, 4 and 5. 4 plus 5, is that greater than the other side? The other side is 3. Well, 3 plus 5 is 9, and that's greater than 3. So this is a possible triangle. I'm going to run out of time here in a sec. So basically it's up to you to check these other lengths. Again, they must be greater than, not equal to, greater than the other side. If it's true, if all three of them are true, you have yourself a triangle. If not, it's not a triangle.